Hello and welcome to Global Math Mentor. Paper 3 is where IB really tests whether you understand math, not just memorize it. Today we are tackling question 1 from the May 2025 Higher Level Analysis and Approach Paper 3, and I'm going to show you how to break it down step by step so it becomes surprisingly manageable. If you want to score those top marks, stay with me. This question is a masterclass. So let's start solving the question. The following question explores features of family of curves. The family is then linked to a homogeneous differential equation. So the curve is given by, let's just write the curve, x and x squared minus 16, and divide the whole thing by x squared plus 16. A1, sketch the curve of y for negative 10 to 10, and it's just a 1 mark part. So remember that there is like a paragraph on top of the exam when you start at paper 3 where they clearly mention like you have to use the graphic display calculator and show the key features and show your working clearly, answer all the question on answer booklet and stuff, like go over that. Like, okay, so I'll be using the graphing calculator to uh, graph this. So this is x bracket x squared minus 16, put a fraction, and x squared plus 16. So I need to set my v window. The viewing window is negative 10. The domain is given negative 10 to positive 10. And I can set this to, let's say, I can do it minus 10 to 10. Again, it doesn't matter. Let's see how the graph looks like. Okay, so this is what the graph looks like. That's wonderful. I need to sketch it now. So let's see the key features as well. So it's negative 10 to 10, and I can check the roots, G-solve, and it's a good thing to check the roots. So negative 4, 0, and then there's a 0, 0, which I can see origin, and then there's 4, 0. And okay, I've got plenty of information about this graph. Uh, I need to sketch it, and sketch doesn't mean like exactly accurate, but the key features should be there. This is 4, and the graph looks like this and this, right? So now I need to check like what's the value at negative 10 and 10. They haven't asked about it, but you can always check these values, x and y, right? That's it. That's the sketch. Okay, next part. State the coordinates of the point where the curve crosses the x-axis. Okay, so I need to give the coordinates now. Minus 4, 0, 0, 0, and a 4, 0, right? These are the answers. Part 3. This is now state the coordinates of the local maximum point and the coordinates of the local minimum point. I need this one and this one. That's the local maximum, and this is the local minimum. Okay. So again, my graphing display calculator can tell me a lot about this. Go to G-solve and just click the max, and that's a negative 1.9434. Okay, I can I can do this. I can copy this, and that will give me my answer. Let's just copy it here. So these are the coordinates for the max, and I can check the local minimum as well. Go to G-solve and minimum. So that's this one. Let's just copy it here. And I need to write my coordinates. So it will help me write my coordinates. So negative 1.94. You can write all the values, or you can give your final answer 3 sig figure. First write them, and then you can give your answers 3 significant figures. So 1.20, this is the local max. This is the max one. And the next one is the min one, which is a 1.94 and a negative 1.20. Okay, so these are A1, 2, and 3. Let's move to the next slide. Part B, state whether the function this is odd, even, or neither. Justify your answer. So in order to check whether this function is an odd function, even function, or neither, you just switch your x with a negative x and see what happens. So this will become a negative x, and then I will have a negative x squared minus 16, and the whole thing divided by negative x squared and plus 16. This becomes minus x. The negative x squared is just x squared, 16, and divide the whole thing by x squared plus 16. So this becomes just the negative of f of x. So whenever a function obeys this property, it's known as the odd function. You might be thinking, if you haven't practiced this part, if f of negative x equals to the same function like f of x, then it's an even function, right? So this one is an odd function. Now consider the general curve given by its y equals to x times x squared minus a. Divide the whole thing by x squared plus a. So it's a general curve. So they have given a constant, and they are saying where a is a positive constant, and x belongs to real numbers. So C part. Given that f of x is this, prove that f prime of square root a is independent of a. Okay, so it's a calculus quotient rule problem. So I can see it's a quotient function. You can rewrite your function first as, let's say, x cubed minus ax. This will convert this into a u over v form, and now go with the quotient rule. F prime x is going to be second as it is, the derivative of first, which is 3x squared minus a, minus sign, then you have x cubed minus ax as it is, and the derivative of x squared plus a, which is going to be 2x. Since a is a constant, so a's derivative is 0. Divide the whole thing by the square of this thing. Now I need to substitute square root of a in place of x. Let's see what happens. This will become a plus a, and this will become a 3a minus a minus. Okay, this, it's better if I rewrite it like this, x squared minus a. You'll see why. It's easier to substitute the square root a value. So square root a times, oh, this is a minus a, so no need to go any further. This will eventually become 0 this side, right? Divide the whole thing by a plus a whole squared. So this will become, this is a 2a and times a 2a, which is a 4a squared. And the denominator becomes 2a whole square, which is a 4a squared as well. Cancel this, and this is 1. Hence, this one does not have a independent of a. Part D. The first part says show that this expression on the left is equal to this, and there is an identity mark in the middle. So we know that I can make the left look right or right look left. Right now it's just a 2 mark thing, so left can be easily made seen like the right hand side. Okay, let's pick the left hand side. So this is 2ax divided by x squared plus a. So I can rewrite it as a single denominator, x squared plus a, and minus 2ax, and divide the whole thing by. So I'm writing this fraction as a single denominator. This will become x cubed plus ax minus 2ax, and divide the whole thing by x squared plus a. One more step, I can write this thing as minus ax divide x squared plus a. And hence, if you factor out the x from the numerator, this becomes x squared minus a, and divide it by x squared plus a, shown. Okay, that's what I wanted to show. So it's just like proving an identity. Next part, hence determine the equation of the oblique asymptote to the curve. To to find the oblique asymptote, the left-hand side is a better form. So you can look at this function. if you have done these rational functions before. So if I have a constant over here, I have a horizontal asymptote in these rational functions since it's an improper fraction. But I have a variable here, x. This thing over here, this thing, is the equation of the oblique asymptote. So you can write y equals to x. That is my, you can say, oblique or the slant. You can write it as well, slant asymptote, right? Okay, now the third part, they're saying write down the coordinates of the point on the curve where the oblique asymptote is parallel to the tangent to the curve at that point. Okay, so we want the coordinates of the point where the oblique asymptote is parallel, and it's just saying write down. It must have to do something with the previous parts. So we just found out that f prime of square root a is 1. So the gradient is 1 at the point where x coordinate is square root a, and we can say that the gradient of the oblique asymptote is also 1. So this will be the same point where your oblique asymptote is going to be parallel to the tangent. Since when lines are parallel, their gradients are same. Okay? So all I need is to find the y coordinate for this point. Let's go find out. Oh, that's going to be 0. Let's take a look. So y is going to be square root a. And when you substitute square root a squared, that's going to be a minus a. And divide the whole thing by a plus a. So this will become 0. The y coordinate is 0. So you can write square root a and 0. That's why they were saying write down. Now consider the differential equation. X squared dy by dx equals to x times x plus y minus y squared, where x is not 0 and y is not equal to a plus or a minus x. So they've given some limitation for this. So using the substitution y equals to vx, the differential equation can be written as this. So this is a substitution we use for the homogeneous differential equation. So before I solve E part, I need to show that top part, right? Okay, so let's go. I pick my differential equation, x squared dy by dx, and equals to x times x plus y and minus y squared. Since y is vx, switch all the y's with vx, but I need to find this dy by dx as well. So let's differentiate it. Dy by dx can be written as v plus x dv over dx. So let's just substitute it in the equation, x squared times v plus x dv over dx. So it's a good idea to solve it with me. Like you can pause and try these questions on your own. And you can always come back and check my work as well. So x times x plus vx. I'm changing all the y's with vx, right? And I have substituted the value of dy by dx in terms of v and x. So minus, this is going to be a v squared x squared. Let's expand the brackets. X squared v plus x cubed dv over dx equals to x squared plus x squared v minus v squared x squared. These terms cancel each other. And I can write my expression. Okay, let me just solve it over here. This is going to be x cubed dv over dx. Put a line over here. Equals to, let's factorize the x out. That becomes, keep an eye on this thing as well. Keep an eye whenever you are solving such results where you have to show something, keep an eye on what you are trying to solve. So we know we can get rid of these and all I'll be left with is x dv over dx equals to 1 minus v square. There we go. Shown, right? Okay, next part, they're saying, like the E part, they're saying using partial fractions, show that this thing can be written as this, where a is a positive constant. It's a 5-mark question. So now I'm out of space. Let's solve it in the next slide. So now we solve part E. Using partial fractions, show that the integral of 1 over 1 minus v square ends up this result, right? Okay, so let's just pick 1 over 1 minus v squared first. And we know that we can write it as the difference of 2 squared, 1 minus v, and 1 plus v. So the partial fractions, these are linear denominators. Both are linear factors in the denominator. So a over 1 minus v plus b over 1 plus v. So you can time both sides with the denominator on the left-hand side. This will end up 1 plus v and plus b times 1 minus v. And you can put an identity symbol over here. It's not necessary, but it just shows that this is an identity equation and which is true for any value of the unknown, which is v in this case. So I can assign values to v to get my unknowns a and b. So a good value should be v equals to 1. Let v equals to 1. This implies that 1 equals to a times 1 plus 1, which is a 2. So a becomes a 1 half. Similarly, you can let or you can assign v equals to negative 1. That will cancel a, and this will imply that 1 equals to b times, and that's going to be 2 again, and b is a 1 half as well. Once you have the values of a and b, you can rewrite the expression as 1 over 2 times 1 minus v plus 1 over 2 times a 1 plus v. And now, since we wish to integrate this thing, so we integrate this expression instead. So now let's integrate it over here. 1 over 2, 1 minus v. I can separate this. Since we can separate in integration, there's a reason I need to show you something. So the derivative of this denominator over here is a negative 1. So you can put a negative and a negative. You can either directly apply the ln integration, or sometimes students use substitution integration, whatever you want to go with. So I'm using the idea, let me just show you, that if you have a function in the denominator and its derivative on the numerator, you can simply write the integration as ln f of x and plus c. So let's use this idea. So this is going to be, so put a line over here. This will turn out negative ln a 1 minus v. I can put the absolute sign over here as well, since we know that the domain of log is always positive. And plus 1 over, sorry, my bad, that's going to be, uh, I missed the half as well. Half, and this will be a half ln a 1 plus v. Okay? And remember, there's a constant of integration as well, since it's indefinite integration. So now I can write this whole thing as 1 half of the natural log of 1 plus v over a 1 minus v. But there is let's put the absolute signs like they have put. There's a problem with this number c. We have to show this in terms of log as well, since you can see that there's a positive constant which is there with the natural log as well. So how do you convert it? You can write this thing as c and natural log of e. Since we know that natural log of e is just a 1. So next step would be, I want to save some space so I can show you that this will end up ln e to the power of c. And if you want to write it like half, because you need to, in any case, take it inside the domain of natural log and with a half coefficient. So next step, you can write it like 1 over 2 and 2 times ln e c, which will become 1 half of ln e to the power 2c. Okay? And that can do the trick. So now I can write half ln, and we know that when there's a plus sign, the logs converts the sum to products. So e to the power 2c times 1 plus v over 1 minus v. So this e to the power 2c, some positive constant, is a positive value. So you can now let e to the power 2c equals a, where a is greater than 0. And finally, my answer can be given as 1 plus v over 1 minus v, which I was trying to show. So remember, students, if you find anything difficult, always go back, rewind, and check again, and do comment in the links so I can know that which parts you found easy or difficult, or always comment, right? So I'll try to answer every comment that you give. If you have made this far, I'm really happy that you are serious about mathematics and you have an interest. Keep it up, guys. Okay, so now they're saying part F, hence show that the solution to the original differential equation may be expressed in the form this, where a is a positive constant. So I know my original differential equation was x dv over dx, and that was equal to 1 minus v squared, which we showed in the very first place using that substitution, right? And this is a separable differential equation, so I can write it as dv over 1 minus v squared integral and dx over x integral. And we already know that we solved this right-hand side just in the previous slide, and its solution was of the form 1 half the natural log of a and 1 plus v over 1 minus v, right? And now this, I'm going to put it equal to ln x. So you don't need to put the constant of integration since you already tackled it. You applied it to the left-hand side. Sometimes we put it on the right-hand side and sometimes we put it on the left-hand side. Don't put it on both sides, right? So that's how integration works. So now we need to show that the solution should look like that expression over there. So first I need to get rid of this 2. So allow me to erase this and take it to this side. And that will eventually become ln x squared. When you have same base logs on both sides, you can get rid of the logs, anti-log them. And so my expression will now look like a times. Okay, now bring back, since y was vx, so you can switch back v with a y over x. So this will become 1 plus y over x, divide by 1 minus y over x, and equals to x squared. Okay, so if you can write it as a single denominator, x plus y over x, divide the whole thing by x minus y over x. And this is equal to x squared. There we go. And you can get rid of these x. So hence, x squared can now be written as a times x plus y over x minus y. And there we go. That's the solution. This is what we were trying to show, that the actual differential equation solution is of this form. So I used all my previous parts result. All the question is connected. So keep an eye on the previous part. So when you are solving these kind of questions on the actual exam, so you have to flip back and see like what's going on, right? Okay, so this is the last part. Now consider only the case where a times this x plus y over x minus y is greater than 0. Okay, so they're saying show that the solution to the original differential equation is this. Okay, so what was the solution from the previous part, which was x squared equals to a times x plus y divided by x minus y, and there was a modulus sign over here. But since they are saying we only need to consider the case where a is greater than 0, so I don't need this modulus sign anymore. Let's just maneuver this and see what happens. So I can try to write it as a polynomial equation. This will become x minus y equals to a times x plus y. So x cubed minus x squared y equals to ax plus ay. I need to make y the subject of the formula, so let's write it like x cubed minus ax equals to x squared y plus ay. I'm just shifting places. So let's factor out the y. This will become x squared plus a. and equals to, from this side, left-hand side, I can switch it here and there, but I mean, you can do this any way you want to, x squared minus a. And you can see that this will end up y equals to x times x squared minus a. Divide the whole thing by x squared plus a, and hence that is shown. And that's the final part done. If you followed this all the way through, you are already thinking like an HL Paper 3 student. Keep practicing, keep pushing. You're much closer to mastering Paper 3 than you think. This is Global Math Mentor, over and out.